Okay, this is from chapter 2 in the Oxford Applications and Interpretation SL textbook, and it's exercise 2C, and I'm just looking at number 6. A garden is shaped in the form of a regular heptagon. It's got 7 sides, and there that's MNSRQPO, so it's around that way there, that one. A circle with centre T and radius 25 metres circumscribes a heptagon as shown in the diagram below. The area of triangle MSQ, so MSQ, is left for a children's playground. So that's going to be the children's playground, and the rest of the garden is planted with flowers. So that's that area, and that area. Find the area of the garden planted with flowers. Now, the way I'm approaching this problem is I'm actually writing, it's quite a long explanation, but there's a lot of repetition just so you can see where everything's coming from. Okay, so here we can see we're interested in this area, that area, and this area here. So I've got a triangle, a congruent triangle, and we've also got this trapezoid here. So we want to find those areas, 1, 2, and 3, and add them up, and that should give us what they're asking here, the garden planted with flowers, the area of the garden planted with flowers. 1, 2, 3. Okay, so the first step is to find the internal angles of the heptagon, and there's a formula which is 180 times n minus 2, and we can double check that. For example, if it was a triangle and it's got 3 sides, n is the number of sides, that would be 3 minus 2 is 1. The internal angles of a triangle is 180. If it was a square, there would be 4 minus 2, and that's 2 times 180 is 360. They're the internal angles of a square. So we've got the heptagon, we've got 7 sides. So to find the sum of the internal angles of a regular polygon, we'll use that. Now it had to be regular, so they've described this as a regular heptagon, so that's good. And so here n equals 7, there's 7 sides, so the sum of the internal angles is 180 outside of 7 minus 2, which is 5 times 180, which is 900 degrees. So all these angles here add up to 900. If we have to find one of those angles, we have to divide by 7 because there's 7 of them. And there are 7 equal internal angles in a heptagon, in a regular heptagon. Here, each internal angle is 900 on 7, which is 100. I'm going to actually take it away from, I'm going to not keep it exact. I'm just going to move through this rounding as I go. 128.57 degrees, and see diagram above. So each one of these is 128.57. Okay, the next step, and have a look at all my writing there. I've been given feedback by my family that my writing's really not that neat, so I'll have to work on doing better writing. This heptagon is a regular heptagon, so each straight edge is of equal length. Okay, so all of these ones are equal length because it's a regular heptagon. So let's just find NS. We just want to find one of them. We know that the radius is 25. Now this angle 51.43, the way I found that was we've got 7 segments, these triangles here, we've got 7 of them. So that angle would be 1/7 of 360 degrees. So angle NTS, that's the T there, is equal to 360 divided by 7 because the regular heptagon is made up of 7 congruent isosceles triangles. Isosceles triangles have 2 equal side lengths, and these angles are also equal. So NTS, this angle T, is 51.43, so I've indicated that there. To find NS, we use the cosine rule. So NS squared, that distance squared, is equal to this squared plus this squared minus 2 times that cosine of this angle. The included angle is 51.43. So there it is, 25. Remember, this is NS squared equals 25 squared plus 25 squared minus 2 times 25 times 25 cosine of 51.43 degrees. Make sure your calculator's in degrees. And then you find that it's 21.69, the 3 significant figures. So this length here, we've just found to be 21.69, so they're all 21.69. Okay, the next step is to use the area sine rule to find the area of that isosceles triangle. We want to know that, we want to know this and that, remember? So we want to find the area of that. We have an included angle, and we know the 2 sides of that included angle, so we've got the area is a half times this length times that length times the sine of 128.57, and that's there. And again, make sure your calculator's in degrees, and you get 183.9 meters squared for that one. So we know that's 183.9 meters squared. This one is a congruent triangle, 183.9 meters squared, so we know those two. We need to find this one now, 3. I've just indicated what we know. So what we know and can calculate so far, we know all this information. We know that's 128.57. Okay, we know these two. The way we know those two, it's explained down here. Basically, it's an isosceles triangle, so these have to be equal because this distance is equal. Two sides equal, remember, and two base angles are equal. So 180 minus 128.57 divided by 2 will give us these two. Okay. Now, since we know this is 25.72, we know that's 25.72. We know the whole angle there is 128.57. So 128.57 minus 25.72 minus 25.72 leaves 77.13, and that's written up down here. So that's there and here. Okay. And so once we know that's 77.13, again, this length is equal to that length. That's an isosceles triangle, which means that angle and that angle must be the same. So 180 minus 77.13 equals a certain number, and that number divided by 2 gives us those ones there. And when you add them all up, that equals 180. We have enough information now to find these two angles here, because we know that OMN, which is that angle there, adds up to 128.57 because all these internal angles add up to 128.57. Okay, so we know all of that. So if we've got 128.57, we minus 51.44, we minus 25.72, and the answer comes up to 51.41. Now, 51.41 is very similar to 51.44 on the other side, so it does appear, I've written here, this is very close to the angle QMS. So the line MQ, this line here, might well be a bisector of this angle. It looks like this line here bisects this angle, which basically breaks it into half. So you've got 51.4 on one side and 51.4 on the other. The reason it's not exact, I think, is because I've rounded so many times to get to this point. We'll just use 51.41 here and 51.41 here. Okay, now we're going to focus on the trapezoid, which is OMQP. We know this angle is 51.41 degrees, and we know that length is 21.69. So what I've done is I've dropped this line down here. That's perpendicular to MQ and also OP. OP is parallel with MQ because this angle 51.41 is also this angle, and because PQ and OM are the same length, so they will be perpendicular. That line will be perpendicular to MQ when I drop it from O. Now I've labelled this as X, and that is why this is now a right angle triangle, and I know the hypotenuse. So if I wanted to find X, I can put sine of 51.41 is X over 21.69, and I get X is 16.954. So I found that height, which is basically going to be the height of our trapezoid. Now I still need to find MQ. Okay, the way to find MQ is that if I call that Y, that's also Y, and this distance here is the same length as that. So let's find Y. I'm going to use the cosine, the trigonometric ratio of cosine. Cosine of 51.41 is Y, the adjacent over the hypotenuse. So it's Y over 21.69, and so Y becomes 13.53, so I found that. So I found MQ. MQ is going to be 2Y plus 21.69, which is 2 times 13.53 plus 21.69. That's 48.75. Okay, the next step is to find what is the formula for finding the area of a trapezoid, and the trapezoid is our MQPO. Well, it's just the area equals, it's the average of these two lengths, the parallel sides. It's the average of those, so we add them up and divide by 2, and we multiply that by the perpendicular height, and we get 597.12 meters squared. That's the area of that trapezoid. Okay, now we're going to wrap everything up. All we have to do is to add up 1, 2, and 3. We found this isosceles triangle and this isosceles triangle. They were the same areas because they're congruent triangles. So that's 1 plus 2, and then we add that to the area that we found for the trapezoid, which is 3. And so our area 1 is 183.9, our area 2 is 183.9, and as we saw just previously, the area for the trapezoid is 597.12. We add all those together and we get 964.92, or 965 meters squared, to three significant figures.